I'm Kajal, Professor of Mathematics, Netaji Subhas Open University. Dear learners, we will discuss today about graph theory, which is the paper 8B part of the postgraduate mathematics course of Netaji Subhas Open University. We have discussed about undirected graphs in the previous lecture. Today we will discuss the directed graphs. In directed graph, here also we have a set of vertices V, set of edges E, and the mapping gamma from the set of edges E to the Cartesian product of vertices V cross V. But the difference is here the mapping of every edge is done to some ordered pair of vertices Vi, Vj. Unlike undirected graph, here we represent two vertices Vi, Vj and the edge say Ek when mapped onto Vi, Vj, it means this is an ordered pair and Ek starts from Vi, goes to Vj, and that is denoted by this arrow. And Vi is called the starting vertex of Ek or the tail of Ek, and Vj is the ending vertex or the head of Ek. And this edge here is called an arc. So, an edge with a direction assigned to it is an arc, which is used to represent a directed graph, which is called in short a digraph. In figure 12, we can see a digraph. Every edge is assigned to a direction, and here we can see that say in V1, vertex V1, some edges are coming out of V1 and some edges are coming into V1. To differentiate these two phenomena, we call this as out degree of V1. Out degree of a vertex is the number of edges incident out of a vertex, and in degree is the number of edges which are coming to the vertex Vi, and is denoted by d plus Vi and d minus Vi. For example, in figure 12, we can see that d plus V1, that is the edges going out of V1 is only one, that is the edge E, and the number of edges coming into V1 is 3 here, which are F, I and H. Similarly, for V2, we see here that here is a self loop which is J. So, D plus V2 is 2, that is J is going out and F is going out from V2 and J is coming into V2. So, D minus V2 is 1. Now, we know the result for undirected graph, that the sum of the degrees of all the vertices is equal to twice the number of edges. Here we see that each edge contributes 1 to the out degrees, the sum of all out degrees, and 1 to the sum of all in degrees. So obviously in any digraph the sum of all in degrees is equal to the sum of all out degrees, and each sum being equal to the number of edges E in G. So we get this equation summation d minus Vi equal to summation d plus Vi will be equal to the number of edges E. Now we come to the term isolated vertex. Similarly, in the case of undirected graph, here also an isolated vertex is a vertex in which the in degree and out degree both are equal to 0. That is, no edge comes out of it and no edge goes into it. So d plus Vi equal to 0 equal to d minus Vi. Then we call it an isolated vertex. What is a pendant vertex? We know that in undirected graph, a pendant vertex was defined to be a vertex of degree 1. So here also a vertex V in a digraph is called pendant vertex if d plus V plus d minus V is equal to 1. That is, if there is any edge coming out of the vertex or any one edge goes into the vertex, then it is called a pendant vertex. Here, parallel edges are defined as two directed edges said to be parallel if they are mapped onto the same ordered pair of vertices. So, like this, in the figure 12, we see that between V3 and V5, there are three edges A, C and B, and their directions are the same. So they are parallel edges in the digraph G. In the same way as in undirected graph, we define here simple digraph which has no self loop or parallel arcs. And if we remove the directions of all the edges from a digraph, we will get an undirected graph, which is called the underlying graph. Here in figure 13, we see the underlying graph of G shown in the figure 12. So this is the underlying graph of digraph G in figure 12. Now this digraph is used in many subjects, many topics to represent the things with more clarity. We will discuss here one of such representations. We all know what is a binary relation. That is, A and B, if two non-empty finite sets, then a binary relation rho from A to B is rho from A to B is defined as a subset of Cartesian product of A and B. So if A and B, AB, this pair belongs to rho, that means that A and B vertices, or here vertices, A and B are related by some relation, some assigned relation rho. So now to represent a binary relation rho on a finite set A, say A1, A2 to AN, by graph, each AI is represented by a dot as a vertex of a digraph, And if AI row AJ holds, say this is AI and this is AJ, if AI row AJ holds, then we draw an edge which goes from AI to AJ. This is done for all related pairs in A. In this way, a binary relation is represented by a digraph. Now we know a relation is of three natures. It can be a reflexive relation, it can be a transitive relation, it can also be a symmetric relation. How to represent that and how we can find whether a relation is reflexive, seeing the representative digraph of it. Reflexive digraph is a digraph which represents a reflexive relation. We know that a relation rho on a set A is called reflexive if A row A holds for all A in A. If A row A holds for all A in the finite set A. So, the representative digraph should contain, if this is the vertex A row A means there is a self loop on the vertex A. And this should be true for all A in A. So clearly the corresponding digraph representing row will have a loop at every vertex. So this digraph is called a reflexive digraph. For example, the digraph in figure 14 is a reflexive digraph since we can see that there are 5 vertices and in each each of the vertices we find a self loop. So this is a reflexive digraph. Now what is a transitive relation? We know a relation row on a set is called transitive if for any 3 elements A row A, B, C in A row B and B row C, A row B and B row C implies A row C. So, the digraph which represents a transitive relation is called a transitive digraph, and in figure 14 we can see the vertex 1 is related to 2. So 1 row 2 and 2 row 3, and we get 1 row 3. So here we get a triangle, but if we see it more clearly, then we can see that 5 row 1 and 1 row 2 holds, but 5 row 2 does not hold. So the digraph given in figure 14 is not a transitive digraph. And next comes the symmetric. We know that symmetric relation is a relation where A row B implies B row A. So similarly, its representation in its digraph representation, we will get an arc from A to B, where at the same time we will get an arc from B to A. Here in figure 14, we can see that 3 row 4, 3 4 row 3 holds, but 3 row 4 does not hold. So this is not a symmetric digraph. And in the asymmetric digraph, we have asymmetric relation means if A row B and B row A both hold, then A must be equal to B. So simultaneously A row B and B row A cannot hold. Similarly, in those digraphs represented in asymmetric digraph can have at most one directed edge between any pair of vertices. But these are allowed to have self-loops. So they are called asymmetric or antisymmetric, and we can see that in figure 14 this digraph G is not an asymmetric digraph because we can see from between 2 and 3 there are two edges, two arcs oppositely directed. So this does not represent an asymmetric relation. Now, with the definition of symmetric digraph in hand, we now define a complete digraph. Complete digraph is of two types. One is a complete symmetric digraph. A complete symmetric digraph is a simple digraph in which there is exactly one edge directed from every vertex to every other vertex. That is, between every pair of vertices, there are two edges oppositely directed. And a complete asymmetric digraph is an asymmetric digraph in which there is exactly one edge between every pair of vertices. So, we can see that in a complete asymmetric digraph, between every pair of vertices, there is exactly one edge. Exactly the same definition was true for undirected graph. So, for a complete asymmetric digraph of n vertices, we can conclude that it contains n into n minus 1 by 2 edges, that is NC2 edges, similar to equal in the case of as in the case of undirected graph. But a complete symmetric digraph of n vertices contains the double of this number of edges, because each pair of vertices, between each pair of vertices there are two edges oppositely directed. So, in a complete symmetric digraph of n vertices, we can have n into n minus 1 edges. This complete asymmetric digraph is also called a tournament or a complete tournament, because in this way, in this representation of digraph, we can see that the a number of teams play games like football. In this way, between every pair of pair of teams, there is a game played and one team wins. So that tournament can be represented by this complete asymmetric digraph. So this is called a tournament. A digraph is said to be balanced if for each vertex the in degree and the out degree are equal. So d plus vi is equal to d minus vi for each vi. Then the digraph is called a balanced or pseudo-symmetric, or sometimes it is called an isograph. So this is true for each vertex, that for that vertex in degree is equal to out degree, d plus vi equal to d minus vi. And a balanced digraph is said to be regular if every vertex has the same in degree and out degree as every other vertex. This is said to be, then it is said to be regular. Now we come to the definition of directed walk. This is also similar to the case of undirected graph, except that the edges are the oriented edges to be oriented from the vertex preceding it to the vertex following it. So the definition is a directed walk from a vertex Vi to Vj is an alternating sequence of vertices and edges beginning with Vi and ending with Vj, two vertices, such that each edge is oriented from the vertex preceding it to the vertex following it, and no edge in a directed walk appears more than once, but the vertices may appear more than once. In the figure 12, we can see a directed walk which is V2F, V1, E, V3, A, V5. So if the arc F is oriented from V2 to V1, arc E has to be oriented from V1 to V3, and A goes to V5 from V3. So it is a directed walk. And in a walk, if this does not happen, if some edge is oriented in the opposite direction, then that will not be a directed walk. But if we ignore the directions of all the edges, then we will get the underlying graph of the digraph in which that will be a walk. So that walk is called a semi-walk. So we can define a semi-walk in this way, that a semi-walk in a directed graph is a walk in the corresponding undirected graph but is not a directed walk. For example, in figure 12, if we consider V1, I, V4, G, V5, C, V3, this is a semi-walk because we consider here I, G and C, three edges. We can see that I, G and C, they are not oriented. I goes from V1 to V4. I goes from V4 to V1, but in this semi-walk it should be from V1 to V4. So this is not a directed walk. G goes from V4 to V5. This is right here, but C goes from V3 to V5, where it should be from V5 to V3. So this is a semi-walk here, not a directed walk. And the semi-path is defined in the same way. A semi-path in a digraph is a path in corresponding undirected graph but not in the digraph. Now, in short, we will discuss about the connectivity of a digraph. This is as we saw that the walk is defined in two ways, directed walk and semi-walk, directed path and semi-path. So connectivity is also defined in two ways, strongly connected or weakly connected. First, the strongly connectedness is obtained from directed paths, and weakly connected is defined from semi-paths. So strongly connected digraph is a digraph where there is at least one directed path from every vertex to every other vertex. So, from between any pair of vertices, there must be at least one directed path. So, then only we can say a digraph to be strongly connected. And if this is not the case, but its underlying graph is a connected graph, then obviously there must be some semi-paths between every pair of vertices, then it is called a weakly connected graph. In figure 15, we can see two graphs. The right hand side is a strongly connected graph. We can see that between every pair of, there are 4 vertices, and between any pair of vertices there is a directed path. We can see it. But in the left side weakly connected graph, we can see that between some pair of vertices there is no directed path. But the underlying graph is a connected graph. It is obvious. So, it is a weakly connected graph, and the second one is a strongly connected graph. We can define the connectedness in digraph in these 2 ways.